Okay, lecture 84, simple harmonic motion. So I was going to go ahead and start on gases, but I think this is a good opportunity to talk about simple harmonic motion and then waves, because we just got done talking about liquids. I want to talk about waves in liquids. Okay? So we'll do a little, probably 2 lectures on simple harmonic motion and then a few lectures on waves, and then we'll move on to gases and really thermodynamics. Okay, so this is not the greatest illustration, but I just want to make the connection between simple harmonic motion and circular motion. Okay? So imagine that I have a frictionless table, okay? And I've got a block connected to a spring, and I've pulled on it so that it has some stretch, and then release it. And so now it's oscillating back and forth kind of into the plane of the whiteboard here, right? Back and forth, back and forth. And we have a projector here shining light, so we see the shadow on a screen right behind it. And the shadow you'll see moving, oscillating back. It really should have been more like this, but oscillating back and forth, right? In front of this oscillating mass, right, I put a little circular table that's spinning in a circle like this, in the direction the little arrow is going, right? It has a little nub on the end of it, right? Such that the shadow of this little nub is going to move in sync with this oscillating mass here, okay? So if you can imagine that in your mind, you kind of see the connection between circular motion and simple harmonic motion, okay? And so if we were to look at the displacement, right, if we were to measure it and say, okay, I got my ruler here, right, maybe I call, this 0, and it's going to go out to a maximum of, say, A, and then also it can go to a minimum of, say, minus A, some distance, right? We'll call that amplitude, okay? So the amplitude is the kind of the maximum distance that the block goes to as it's oscillating back and forth on the table, right? Since it's frictionless, it's just going to keep doing that forever, okay? If I were to graph this, say versus time, okay, where this is x, the displacement from the 0, the center. 0 would, of course, be where the mass would sit if the spring was unstretched and uncompressed. You could call it its equilibrium position, right? So you start from there, that's where it naturally sits, and then I stretch it out and release it. It's going to go back and forth between A and minus A. A and minus A, okay? Does that make sense, what we have going on here physically? Yeah? Okay, so now let's see how to describe this stuff mathematically. Well, what kind of curve does this look like? If you had to guess what the form of this curve is, it keeps on going forever, right? Do I mean a wave? Well, yeah, I suppose some people call it a wave, but what mathematical function do we know of that might describe this? Let's have a look at it. Here at t equals 0, its amplitude is at the maximum amount, right? The displacement is at its max, which is A, right? So if A is 1, right, this is, say, 1, and this is minus 1. What curve might this be described by? Can you think of any functions? X squared? Is this the graph of x squared, or t squared, rather? No? What might describe it? Sine, right? But sine is at 0, right? Or 0, right? Sine of 0 is 0. This is at 1, or A, right? At 0 degrees, right? Or t equals 0, rather, right? So wouldn't this better be described by, say, a cosine? Yeah. So x, as a function of t, that's the displacement, right, is equal to A times the cosine. And now inside here we got to put some terms, right? Omega times t, right? Because remember, one period from here to here, let's say, right, corresponds to going through from 0 to 2 pi, right? So this distance, if this was in radians, this would be 0 to 2 pi right here, right? So we need some way to go from radians to time, okay? And the way we're going to do that is some measurement that gives us radians per second, right? And we're going to call that omega, okay? It's oftentimes called the frequency, okay? So if I take omega times the time, whatever this time is here, right? Call it t1, right? t1 times omega must be equal to 2 pi, okay? Okay. But I'm also going to add in a kind of an arbitrary term, a little delta, right? Just some constant, because maybe I don't want to start the wave off exactly at the maximum value. Maybe t equals 0 is like here, okay? If that's the case, then this delta allows me that possibility for that, to start it off at any point along the phase of the wave, okay? So that's what these terms are. And so this, generally seems to fit the picture of what would describe it, okay? So now what we're going to talk about is what about the velocity? So if this is the position as a function of time, can we write down an equation for the velocity? And we can, but let's think about it a little bit conceptually what it might be. Okay? So if I look at, say, a point on here initially, right? How would I get the velocity? I would do some displacement. I'd say, you know, maybe let me just extend it backwards a little bit. Obviously, it came from something back here, right? I could pick a point right here and say pick a point right here, right? And so I call this, you know, x1, and I call this x naught or something, right? And so the velocity is going to be the delta x divided by the time it took, right? And that's going to be described by a line which looks like this, right? Yes? Yeah. If I allow this delta x to be very close together, such that it's right around this 0, you can see that this is pretty much flat. A line whose slope is flat, right? Its slope is 0, yes? So delta x is approximately 0. It doesn't change very much in this little time interval, right? So the velocity up here is effectively 0. And this corresponds, of course, to the end point of the stretch, right? As it's oscillating back and forth, it's headed in this direction, and it slows down to a stop. I did a double oscillator. Right, let's say this is the block, right? This is equilibrium now. It's moving in, compresses, it goes back, passes equilibrium, then it slows down and stops at some point. Now the velocity is equal to 0, but the amplitude is maximized, right? We're as far away from the wall or whatever we tethered to as possible. So that's this point right here. When you're at maximum amplitude, your velocity is 0, because you're slowing down to turn around in reverse direction, right? Now we're reversing direction and headed this way. So here our velocity is decreasing, or it's negative in nature, right? It's going in the opposite direction. It's going in the minus x direction, right? So if it's 0 here, right? Let me see if I can superpose some graphs. It's 0 here, right, for the velocity. The green will be the velocity, all right? Black will be the position. At some point, what is it here, right? Here the velocity is maximized, because what happens after this point? It starts slowing down to turn around again, right? Here it's 0 again, right? So here will be 0 again, yes? This is the maximum velocity. I don't know whether to draw it positively or negatively. I'm just going to go with my gut here and draw it positively. So we'll say it's at some maximum velocity. It doesn't have to be the same amplitude, right? I'll say maybe this point here. Here it's 0 again. So we're going to speed up. Well, actually, no, it should be the other way, right? Because it's headed in the negative direction. So it should be going down like this, right? And at this point here, let's say, that's still not right. Right here, we'll say is when it's at its maximum velocity. And then it's going to turn around like this, right? And it's going to do the same thing. This will be another point where the velocity is maximized. So we'll go up to maybe here. Here the velocity will be 0 again, so we'll go down, something like that. It's not the greatest graph in the world, but it'll have to work. So this is the velocity, right? So velocity x, right? So if it's 0 here, what do you think the mathematical? You can see it's still some kind of sine wave of some sort, right? Whether it's a cosine or a sine depends on where the starting point is, right? Yeah. Turns out it's going to be a sine wave, okay? And it'll be negative, right? So we have to multiply this times a negative number, which means that I really should have drawn it the other way, so that because we have the negative sign in there, right? So let me just fix the drawing. There we go. So this is the velocity curve. But we need a negative sign in it to make it negative, right? So it'll be minus, and it'll turn out that it's equal to minus a times omega, okay? And I'll justify that in just a second, times the sine of omega t plus delta. You see, it still has the same period, or the same frequency as the original wave for position, right? The levels are different, right? This would correspond to, V max, and this is kind of minus V max over here, minus V max, okay? Why do we have this factor of omega here? Well, remember, this has got to be in units of velocity, right? And so if I just had minus a, well, a is an amplitude. That's a displacement, right? Yeah? So displacement doesn't have the right units to be a velocity. But frequency is 1 over time, right? Yeah. So we have delta x times 1 over time. gives you a velocity, okay? So it makes sense that we have this omega here. Really, if you had calculus, this would be trivial, right? We'd just take a derivative and we'd be done with it, okay? So that's what the velocity looks like. And you can make the same argument for the acceleration, okay? If we were to look at this curve here, we'd be like, well, here the acceleration is 0, right? Here the acceleration is maximized. Here it's maximized, but in the other direction, right? It's going to have the same form as the original wave, right? So it's going to be a cosine again. Cosine of omega t plus delta. Now what about the terms in front of it? Well, now we need something that looks like distance per time squared. So we need another factor of omega in here. So this would be minus a omega squared times cosine. Okay? So these are the equations to describe the acceleration, right? Yeah. As a function of time, the velocity as a function of time, and the position as a function of time. Okay?
All right.
Remember I said this was a spring, right?
Yeah.
And what do we know about springs? Who remembers the law that governs the forces on a spring? Anyone remember what that law is called? Hooke's law? You remember Hooke's law?
Yes.
Hooke's law says that the force is equal to minus k, where k is the spring constant, right?
Yeah.
Really stiff spring has a very large k, right? Times x, right? Where x is the displacement. Okay, this says the force is going to pull in the opposite direction, that's what the negative sign is about, to the stretch that you make on the spring. So if I stretch the spring like this, the force is going to pull back, right? And the farther I displace it, the more it pulls, right? You've played with a spring before. You know that you can pull it a little bit pretty easily, but you can't pull it very far before it's too strong, right?
Yes.
Yes?
Yeah.
Same thing with compression. If you ever use those hand gripper things, right? Those are just springs with a very high spring constant, okay? Such that it's hard to squeeze them closed, right?
Yeah.
So, but force, of course, is mass times acceleration, right? This is mass times acceleration. Well, we have a term here for acceleration. So if this is the equation for acceleration, it goes in here, right? Let's just divide both sides by m. Let's just move the m over here, right? Now I have a is equal to minus k over m times x. Well, what is this? A here was just equal to minus a omega squared. Well, actually, the a we lose. Hang on a second. Minus omega squared. A times cosine is just x, right? As a function of time. Yes?
Yeah.
So the acceleration is just minus omega squared times the original function for the position, right?
Yeah.
For the displacement. So looking at this and looking at this, right? Here I have an x, here I have an x, here I have a negative sign, here I have a negative sign. Omega squared must be equal to this k over m, right? And it is, right? That tells you what the frequency of a spring is. Omega squared is equal to k over m. So if you want to know what the frequency that a spring is going to oscillate at, then you have to know what mass you're going to put on it and what the spring constant is, and you can determine what frequency it's going to oscillate with. It'll have some characteristic frequency, okay?
All right.
If you have a heavier spring, right, the frequency is going to be higher. It's going to oscillate like this. If you have a smaller spring constant, a lower spring constant, right, it's going to be a slower frequency that it oscillates with, right?
Yeah.
Okay? I was thinking about putting some discussion in on a driven oscillator, it's called. Because when we talk about light, that will be useful for this purpose, but I think I'll save it for that time. Because it's kind of complicated, but you can imagine this, right? If I have this spring, it's on a frictionless board, and it's oscillating back and forth at its natural frequency, right?
Yeah.
And I come along and I smack it every time with some frequency, right? If I smack it at the same frequency as its resonance frequency, then it'll get bigger and bigger amplitudes, right?
Yeah.
It's a little bit like that trick kids do in the pool where they all wave in sync with one another to make giant waves, right? But if you don't drive it at the right frequency, what happens? Well, you know, it's oscillating back and forth. You know, if I smack, 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 then you're going to drive it to bigger and bigger amplitudes. But if you drive it like, if it's oscillating like this, and then you drive it like, right, you're going to totally destroy its oscillatory motion, right? So you have to be on resonance with the natural frequency of the system, you see?
Yeah.
Okay? And so for something with friction, right, it's a very sharp resonance indeed. You have to drive it pretty much at that frequency or you're going to destroy its oscillatory motion and its amplitude is going to decay quickly. Okay?
Okay.
But if you drive it on resonance, then you can get really large amplitudes. Okay?
Yeah.
But the mathematics of that discussion are a little bit complicated, and I think I'll probably just save it till we do talk about light. Okay, so where are we at? We have this kind of final form. I'll put it over here. I'll write that x is equal to a cosine omega t plus delta. V is equal to minus a omega sine omega t plus delta, and that a, the acceleration, is equal to minus omega squared x, which is the same thing as minus k over m x. All right? Yeah, that looks good. So what I want to do next, is use our trigonometry skills, in particular a couple of identities, which I'll maybe write over here for reference. Recall that the sine of theta plus phi is equal to the sine of theta times the cosine of phi plus the cosine of theta times the sine of phi. Remember that? It's the sum of two angles formula. Also, the cosine of theta plus phi is equal to the cosine of theta times the always mess that up, times the cosine of phi minus the sine of theta times the sine of phi. Okay? We have these two trig identities that we can use, right? And what I want to do is I want to talk about, instead of this amplitude, I want to talk about the initial conditions. Because it may be that you stretch your spring out, not to its maximum amplitude, but just some other point, right? And when I release it, I don't just release it with no velocity, I give it a push, okay? So I give it some initial position and some initial velocity. That's a more usual situation, and it's useful to have equations that will describe it in terms of these initial conditions. So, initial conditions, x naught and v naught, okay? That looks like v sub 1. Let me just make that. There we go. Initial position, initial velocity, okay? So we can use these identities to get the equations into that form, okay? So let's start with the position function and rewrite that using this identity, right? Where my theta and phi are basically the omega t is the theta and the delta is the phi, okay? So x, as a function of time, is equal to, we use the cosine identity, the cosine of omega t, we need an a, of course, a times the cosine of omega t, times the cosine of delta, right? Minus a times the sine of omega t times the sine of delta, okay? Now, to find out what x naught is, what do? You set t equal to 0, right? Yes. That's what we mean by that. So x of 0 is equal to what? Well, what is the cosine of 0?
It's 1.
It's 1. So we get a cosine delta minus, what is the sine of 0?
0.
0. So there's nothing. That's it. So here we have x at time 0 is equal to this. What does that mean? That means that x naught is equal to a cosine delta. Okay?
Okay.
Now let's do the same thing, but do it for the velocity. So the velocity we'll write as, remember there's a minus a omega multiplied times it, okay? So we'll have minus a omega times the sine of omega t times the cosine of delta, because we're using this identity now, right? Because the velocity is a sine function, yes?
Yeah.
Plus, but we have a minus a omega, so it's minus a omega times the cosine of omega t times the sine of delta. Okay? Now we'll ask, this is v of t, so let me just write that to be clear. So what is v of 0? Well, v of 0 will be our initial velocity, right? So whatever it is, that's equal to v naught, right? Well, what is the sine of 0?
No, 0.
0 again, right? What is the cosine of 0?
1.
1. So we have, this is equal to minus a omega sine of delta. Okay? So we have that v naught equals minus a omega sine of delta. But what will be more useful to us is to write this as v naught over omega is equal to minus a sine delta. Okay? Because if we use that, we can go back. Let me just erase this, erase this. Let's look at the first equation here, right? X of t is equal to a cosine omega t cosine delta. You see the a cosine delta here? Yeah? This part and this part, right? These two pieces? That's just x naught, right? So this can be written as x naught times the cosine of omega t. All right? And then we have this minus a sine delta, right? Well, minus a sine delta is v naught over omega. You see that?
Yeah.
So minus a sine delta is just v naught over omega. So that becomes plus v naught over omega times the sine of omega t. Okay? So now we have a new equation in terms of the initial conditions, which I'll write over here just to catalog them. V of t, x of t equals x naught cosine omega t plus v naught over omega times the sine of omega t. Okay? We can make the same substitutions in for the velocity function as well, right? Because here we've got a minus a omega, or excuse me, a minus a cosine delta. Well, that's, okay, here's what we're going to do. We're going to move this over here because it's going to have a negative sign on it. So let's do this one first, okay? Here we have a minus a omega sine delta. So I guess I could have put this back in, right? That's going to be v of t is equal to the minus a omega sine delta is just v naught. So that's v naught times the cosine of omega t. And then this term here. We've got a minus a, well, we've got an a cosine delta, which is our x naught again, right? So that's minus x naught. But we have an omega here, right? Omega times the sine of omega t. So I think that is right. So that gives us our velocity function. V of t equals v naught cosine omega t minus x naught omega sine omega t. Okay? So two forms of the equation. One in terms of the amplitude and the phase, which you're not likely to know. The other one in terms of the initial position and the initial velocity of the mass. Okay? And so this is the one that you would use to solve real problems involving a mass attached to a spring, right, oscillating on a frictionless table, right? If we had friction, there'd be dissipation, and these solutions would not quite be right. Okay?
All right.
It also wouldn't be right for a spring hanging, right? Because now we have gravity, right? So we have this additional component we have to add in there. So there's another acceleration that we didn't account for here. The only acceleration we accounted for here was that of the spring. Okay? Let's talk for a second about the energy of this system, okay? In particular, the potential energy, because as I stretch that spring out, I have to do work to stretch it, right?
Yeah.
And so remember that work is equal to the force times the, we'll call it delta x, right, the displacement, okay? And so if I were to look at this, and we know that the force is minus kx, we'll call it, okay? The force versus displacement, right? So this is our x-axis, okay? And so we'll assume that we displace it out to some distance. We'll just call it x here, okay? The force is equal to minus kx, right? So ignoring the negative sign for the moment. Move the point, there we go, okay? It's linear, right? Because this is the equation of a line, right? And so the work is just the area under this curve, right? So let me just draw a little dotted line there, and we're looking for the area under this curve. Well, that's the area of what? What shape is that?
Triangle.
That's a triangle, right? So the work in this case is 1/2 times the base. Well, the base is what? The base is just x, right?
Yeah.
Times the height. Well, the height is what? That's this f, right? That's minus kx. So that's minus kx, right? So that's equal to minus 1/2 kx squared. Okay? And you'll remember that the potential energy, U, is equal to minus the work, right? So this is equal to minus that, which is just 1/2 kx squared. Okay?
All right.
And so what shape describes this? What's this graph going to look like if I graph the potential energy versus displacement x? So here's the x-axis. This is the potential energy, U. What's this going to look like? U is equal to 1/2 kx squared. What is that called?
Parabola?
Parabola, yes, exactly. If we choose the initial potential energy to be 0, then we can have it sit right, the vertex be right here at 0 at the origin. Okay? So here we have a parabola, right? If we assume some initial amplitude, call it A, right? And this would be, of course, minus A. Then let's just take that up to here. It's not the most symmetrical graph, is it? Let me see if I can make it a little better. All this minus A, right? These are equidistant, even though they don't look like it. That's just my bad drawing skills. right, the energy, the total energy, will be this value here, right? And that will be equal to 1/2 Ka squared. Okay?
All right.
And remember what I told you about how to think about these potential energy surfaces. You think about the dynamics of the system as if this were a real well. Okay? And we imagine that we have a marble starting out here at this position, right?
Yeah.
And we release it. What's it going to do? It's going to roll down the hill, right? Get to the bottom, and then start headed back up the hill again, all the way up to here. And then we'll just continue that. Then it'll roll back and forth, right? Where is its velocity maximum at? Where is it going fastest at? The top of the hill, the bottom of the hill, the middle of the hill? Where?
At the bottom.
The bottom of the hill, right? So here's where we get V max, right? Where's the velocity minimum?
At the top.
At the top, right? But put two places, here and here, right? So this is V equals 0. This will be where V is equal to 0, right? And so the way we usually think about this is that, remember, the kinetic energy is, what is the kinetic energy equal to? Kinetic energy, which we usually abbreviate with T for some reason. I don't know if I've ever figured that out, but T is equal to 1/2 mass times the velocity squared, right?
Yeah.
So it's this interplay between kinetic energy and potential energy, right? When it's up here at the very top, all the energy is in the potential energy, right? We release it, it starts rolling down, and so the potential energy is decreasing. It reaches a minimum here. This is the minimum potential energy, but it's also the maximum kinetic energy, right? Because the velocity is maximized, right?
Yeah.
So now all the energy of the system is in the kinetic energy, right? And then it starts rolling back up the hill again, so it's gaining potential energy again. It means its kinetic energy is decreasing, right? And so that's kind of the dynamics of it. So you can think of it, the oscillating spring, right? Where was the velocity 0 at?
Top.
Well, for potential energy. Where was it with the spring, though? Was it in the middle at equilibrium? Was it at the far end point, the compressed end point, or somewhere in between? Where was it velocity 0 at?
The beginning.
At the most stretched portion, right? That's when it's turning around, right? So this, right, corresponds to the maximum amplitude for the displacement, right? So up here, right, if I were to draw a little picture of my spring, right, it would look like this. It would be, let me try to draw it where it looks really stretched. Right? Here's my box, very stretched. Here, where the velocity is maximized, right, that's right at the equilibrium. So that's the unstretched spring, right? Something like this, right? Whereas over here, and then I'll put my little mass there, over here, it's not stretched maximally, but compressed maximally, right? So here, it's very tight, right? Can you see that? Equilibrium, that's where it's moving fastest. Here, where it's moving at 0 velocity, is it when it's stretched as far as it'll go before it turns around and goes the other way? Or here, when it's compressed as far as it'll compress before it turns around and goes the other way? Okay? So these are the three positions of relevance to note in this curve, okay? And so now we've kind of thought about this in terms of the potential energy surface as well. And I think that's all I was going to say about an oscillating spring, right? It's a good description of simple harmonic motion. It's about as simple as it gets, actually. I think next time we'll talk about a pendulum, which if the oscillations are small, you know what a pendulum is?
Yeah.
Right? If the oscillations are small, so I'm not like pulling the pendulum way up here and releasing it so that it's doing like this, but if I just small oscillations like this, they can be described by simple harmonic motion. Very similar to this, okay?
Okay.
And so we'll talk about that next time. Any questions?